Okay.
Um,
Okay. So people can see her screen and all that, right?
yeah. Can you guys see just the portion of the PowerPoint slide?
Yeah, I am.
Okay.
Yeah, I'm seeing that. Yeah. Okay, so let us get started. I am recording the public session, and then I guess the private session, I will stop the recording at that point of time. So this is the first thesis defense I'm attending where there is no free food. And so it's not very clear how good it's going to be for the student. I had to make my own coffee. That's very bad. But so anyway, this is Niharika. She is one of our own undergraduate students. She received, I believe, the Outstanding Undergraduate Student Award for her bachelor's. And she has been also doing this 4+1 degree. And this is her MS thesis work that she's going to present today. And I believe after this, she has a job lined up at LinkedIn in San Francisco. Okay, take it away, Niharika.
Thank you so much for the introduction, Dr. Rao, and thank you everybody for coming today. This thesis is based on a joint effort done in the lab. It's been going on for the past 2 years. So today I'm going to present my thesis called A Study on Generative Adversarial Networks Exacerbating Social Data Bias. My chair is Dr. Subarao Kampambati, and my committee members are Dr. Juan Liu and Dr. Lydia Manikonda. So generative adversarial networks, or GANs, have taken the world by storm with their ability to create realistic synthetic data. And in a world where deep learning models are still very data hungry, and they require massive amounts of data to train with high accuracy, this has been quite the blessing for machine learning practitioners who are facing the data scarcity problem. The way that they use generative adversarial networks is to train GANs to create more synthetic data from the existing data that they do have, and then just take all of the synthetic data generated to augment their data sets. This is useful when acquiring real data of sufficient size is just too expensive or perhaps infeasible, such as with privacy constraints. So this technique has received a lot of praise in both the machine learning community and the tech world. But it's not actually quite clear that the people using and praising this approach realize how dangerous it can be. If GANs worked perfectly, then they would capture the distribution of the real world data. All machine learning models are designed to try to capture the patterns that exist and learn from them. But this means that machine learning models should be picking up on any biases that exist in our real world. And these biases are often not favorable, such as those that exist along social dimensions. Again, this would be if GANs were to work perfectly. They would take all of the biases in our world and perpetuate them. However, GANs go a step further to make things worse. They don't actually perpetuate the bias, they amplify them. GANs have a failure mode, which causes them not to actually capture the distribution of the real world data, and instead something like a caricature of the real world data. But before we can talk about why this happens and how, we should talk about what GANs actually are and how they work. So generative adversarial networks are a stacking of two smaller neural network models. One is a generator and one is a discriminator. This is an adversarial game because each player's motivation is in direct opposition with the others. We'll use a generator network to create the actual synthetic data and the discriminator network to make sure that the data looks realistic. The best way to understand this is through an analogy. This well-known, most famous analogy for GANs is to consider each network as a counterfeiter and a cop. Sorry, excuse me, did somebody put something in the chat? Okay. So the generator is a counterfeiter network and the discriminator is a cop network. The motivation of the counterfeiter is to create real world looking currency. So it's trying to create realistic synthetic data. The cop's motivation in this game is to be able to identify when it sees a fake data point and when it sees a real data point. In this case, the discriminator will provide something like a realness score between 0 to 1 of how real or fake it thinks an image is. And the discriminator network is going to train based on thousands of examples, both from actual real currency and from the counterfeited currency. So over time, with these thousands of examples, it'll train itself to be more and more accurate so that it will be able to maximize the realness score that it assigns to the real minted currency and minimize this realness score to the currency that is counterfeited. This is where the analogy will fall apart though. The generator network doesn't quite behave like a normal counterfeiter would. A regular counterfeiter gets to see what real money looks like, but the generator in the GAN only ever gets to see some semantically meaningless input, such as random noise. The only thing that it has to go off of to train its images to become more and more realistic is the discriminator's feedback. So it'll train to make its images look more real to the discriminator, and it's maximizing the realness score that the discriminator gives to its generated data points. The game will eventually end when the generator can learn to create data that is indistinguishable from the real world distribution. GANs are explosively popular in part because they're very easy to scale up to images, and also they're readily available off the shelf. Here are two of the most popular GAN architectures, and they both have GitHub repositories with several thousand stars. The DC GAN, or the Deep Convolutional Generative Adversarial Network, has the structure and objective function that I described in the previous slide. Another variant of GAN is the cycle GAN, and we'll stick to talking about DC GANs for now, but we'll come back to talking about cycle GAN a little later. But first, I want to present an image and pose a question in the audience's mind. What do these images have in common? Well, to start, you might notice that some of these faces don't quite look real, and they might even look a little ogreish, as my chair will call them. And that's because these aren't actually real faces. They're GAN generated faces, but you might also notice that there isn't a lot of diversity in them. These are faces that are generated by a GAN trained on a data set of engineering professors in the US, which is unfortunately a heavily skewed distribution along race and gender. So the hypothesis of this work is that when a feature is biased in the training set, so if we have some sort of skew and bias in the real world, the GAN that's trained on this data will amplify the biases along that dimension, meaning for the majority, it'll overrepresent these examples, and for the minority, it'll underrepresent these examples when it creates its generated distribution. But just a note, not all biases are the same. That hypothesis does make a pretty blanket claim about whichever dimension the distribution may be skewed along, but we don't necessarily care about all of these dimensions of bias. This bias could exist in pretty meaningless features such as lighting for facial images or facial expression, accessories, hairstyle. But the only real ethical consideration that we want to bring attention to is when a GAN picks up on social biases, and specifically when a GAN picks up on sensitive social biases. So these sensitive features we define as social characteristics that have historically been discriminated against, often against a minority, and which ought to be legally protected. So our work will have a scope of investigating bias over race and gender. So to append to the hypothesis, this means that for facial data sets, which are often skewed along race and gender, GANs will actually exacerbate along those axes. And one last note, since this work is meant to talk about the ethical considerations of an approach, we should talk about the ethical considerations of our approach used in the experiment. So using photos to measure human characteristics, or something called physiognomy, has a pretty ugly history. In the 19th century, in the context of social Darwinism, it was used to give some rational, logical metrics to discriminate against minorities, criminals, anybody who is deviating from the social norm. And furthermore, neither gender nor race can actually be ascertained from somebody's appearance. We'll use some pretty crude metrics of the masculinity and femininity of facial features and the lightness of skin color as decided by humans. But again, this is just a rough metric. It's not going to give an accurate representation of gender nor race. But we're using this to illustrate our argument that GANs will pick up on and amplify data biases. This work isn't actually advocating for the use of facial data at all in machine learning, but rather just trying to use facial data as an illustration. Since society today is attuned to picking up on gender and racial biases, we're going to use a data set where this is pretty easily detectable, biases along gender and race. The purpose of this work is primarily just to caution practitioners who are using this technique about the dangers. And without further ado, we'll start with the actual discussion of the experiment. So if we were to train a GAN to imagine an engineer, what would it come up with? We predict that it will actually skew its new generated data even further toward white males, since the set of US engineering professors is a data set that is already highly skewed toward white males. So the first step in this training process is to collect the data. So we use a test browser to scrape from the web pages of 47 different engineering schools across the US, and we make sure that we remove all noisy images. We're defining this as any time where there's an image that isn't of an engineering faculty face. So this could be where the engineering professor had a directory listing but did not have an image, so the university replaced it with a university logo or a ghost image. It could also be any images where a face can't actually be recognized, since this was an important step in the pre-processing. It could also be where there was a clearly visible face, but it wasn't of an engineering professor, such as when staff find their way onto the faculty directories as well. So after we removed all the noisy images, we were left with over 17,000 headshots. We pre-processed the data to make sure that the discriminator was only picking up on meaningful samples. So this means that we wanted to minimize the semantically meaningless features it could pick up on to decide whether a data set, whether a data point was from the engineering data set or not. So this could be something like the lighting or the background color, since most of these are headshots. So we crop the images to the face just to make sure that the discriminator is only picking up on features that correspond to the face. We then train a DC-GAN on 3 random initializations so that we can receive 3 different samples. Here are some samples of those 3 randomly generated distributions trained on the engineering faculty data set. Now, again, we can kind of see that we already have some biases in the data. There isn't a lot of diversity in terms of race, and if you look carefully, there doesn't seem to be a lot of diversity in gender either. But to actually evaluate this data, we'll ask humans to help measure those distributions and their diversity. So we go on the Amazon Mechanical Turk platform to ask humans to annotate 50 images that are randomly sampled from one of the 4 distributions, either the original distribution of real-world professors or one of the three generated distributions trained by the GAN. So each Turker on the platform receives the following question for each image. Select the most appropriate description. They have to select one of the options that is our gender metric and one of the options that is our race metric. So they'll answer whether one of the faces that they see has mostly masculine or feminine features or an ambiguous option, or whether the skin color is white or non-white or an ambiguous option. This experiment design is a between subject design. This means that each of the humans that are labeling a data point are only looking at one of the data sets. So if we ask a Turker to annotate a real world professor, they're never going to be asked to annotate a fake generated professor. And here are the results of that study. For the generated distribution on the bottom, we averaged out all of the answers for the 3 generated distributions. So it's pretty clear just from the visualization that the GAN does learn to underrepresent the minority along the gender axis. It goes from having 20% feminine features in the original professor data set to only 6.67% in the average generated data set. Same thing goes for race. It actually almost misses the non-white mode entirely, creating just barely over 1% of professors that don't seem to have a white skin tone. In this case, we used a majority thresholding to label the images, meaning we would only classify one of the images as having feminine features if the majority of the Turkers we asked believed this to be true. Now, these results already look pretty statistically significant, but just to make sure, we did a 1-2 proportion Z-test. This is where the alternate hypothesis was that the proportion of the minority features in the generative distributions, either feminine features or non-white skin color, were less than the proportion of the minority features in the original training distribution. And we do find that the p-value is extremely small, so this is a very statistically significant result. We also look at what the classifications would have been if we used a different threshold. So on the x-axis of all of these graphs, this is the number of votes that it would have taken to classify an image. And on the y-axis is the proportion of images that would have been classified as having a certain label. The main focus here is that the orange label is the female class and the blue label is a non-white class on the right. And this is a metric of confidence. If we look at the original data, that's the two left graphs on both orange and blue. We know that whether we had the voting threshold be 2 or 15, it didn't really seem to matter that much. This means that the Turkers are pretty confident on which images are images of females and which images are images of males, and also white and non-white. However, in the generative distribution, this isn't the case. You can see that the number of images that get marked as female significantly drop as it requires more Turkers to vote for that label. And the same thing happens for the non-white features as well. So this is a confidence metric. It means that Turkers are just not as confident when a generated image belongs to a minority class as they are when the images belong to the majority. If you look at those gray bars in the right charts, you'll see that those don't go down, only the minority class does. So why would this have happened? Well, there are two possible reasons. The first one is that humans who are doing the labeling just have an inherent bias. So they'll default to male or white when an image is pretty ambiguous. But notice that we had the ambiguous option as well, and the confidence in the ambiguous option, can't tell, also vanishes with an increasing threshold. There's no distribution where there's an image that is marked as being ambiguous by over 4 people. So the second alternative is that the GAN truly is just much better at producing realistic patterns when they belong to the majority. So it's much better at producing realistic male faces and white faces than at producing realistic female faces and non-white faces. It just doesn't seem to learn how to create these modes as effectively. And we also supplement our results from the human annotations with an automated process. We use the Microsoft Azure Cognitive Services Face API. This commercial gender classifier we run on 1,000 images over 5 random initializations of DCGAN rather than 50 images over 3 random initializations. And this is just because since it's an automated process, we can give it a much higher sample size. And this is a statistically significant result, although it's not as drastic of a change. We only drop from 16.5% female to 11.38% female, but nevertheless, this is still a shift in an underrepresentation of minorities. And since the sample size was 5,000, we have a very statistically significant result. So these results show that when we ask a GAN to imagine what it thinks engineering faculty look like based on the engineering faculty data set of US professors, the GAN will collapse to generate more masculine features and more light skin tones. Why would something like this happen? Well, as I mentioned, this is a failure case of GANs. GANs are not designed to capture any distribution other than what exists in the real world data. This failure mode is called mode collapse. It's well known and well studied, although there hasn't been much said on how mode collapse influences or how skewed data sets will influence mode collapse. So first, let's talk about what mode collapse is. It's where the diversity of the generated distribution is actually far lower than the real world training distribution. Mode collapse can happen in 2 ways. There's complete mode collapse, where the generator will learn to map many different inputs all to the same exact output. So in the end, it's going to create identical images. This version of mode collapse, complete mode collapse, is actually quite rare. And even when it happens, it's pretty easy to detect that something has gone wrong. The much more pernicious problem is partial mode collapse. This is where the generator, instead of learning to map various inputs Z to the exact same image, it'll map various inputs Z to very similar colors, textures, and patterns. In this case, we had trained a GAN on all of the digits 0 through 9, but it only seems to pick up on 1s and 8s. This means that even though the images aren't exactly identical, the modes are still, there's still more probability of having certain modes, 1s and 8s, than other modes, such as every other digit. Mode collapse is where the generated distribution does not match the data distribution. In theory, over infinite training examples, you would see perfect convergence of the generated distribution to the data distribution. So if you were to train a GAN on a data set with 2 modes where both of the modes are distributed uniformly, then we would see over an infinite time period that the distribution converges perfectly. This means that the generator would learn a mapping of its inputs Z so that it assigns the perfect amount of probability mass to each of the modes so that they correspond with the distribution of the real world data. However, in practice, we don't have infinite training examples or infinite time. So we'll see that the GAN will collapse to creating one mode more than another mode. This means that the generator is learning to map many more inputs of Z to a particular mode and not mapping enough inputs Z to a smaller minor mode. In this case, both GANs are meant to be trained on a uniform distribution between modes, so both modes are equally probable in the data set. There's an explanation for this. Che et al. Explained that the areas near the missing or minor modes are rarely visited by the generator, and because they're rarely visited by the generator cannot learn to create them. It's kind of a loop. If the generator does not map a lot of inputs Z to a minor mode, it can't learn to make that mode any better. And that's because the only way for the generator to learn is based on gradients in the discriminator. And the discriminator will only give its feedback for the mode that it sees. So by definition, the generator is creating images in minor modes much less often. So it'll receive feedback for these minor modes much less often. So in the end, it'll only map a very small set of Z inputs to one mode and a large set of Z inputs to another mode. This would have been an example of mode collapse on a uniform data set where some modes are equally probable in the data set. And mode collapse already poses a difficult challenge when the distribution is uniform. We also hypothesize that mode collapse is even worse when it's skewed, and that if there's a major mode in the original training distribution, it will become an even bigger major mode in the generated distribution. So to summarize that last slide, mode collapse is a consequence of insufficient feedback from the discriminator from a particular mode. Just to give some intuition on why we think that this should happen, that mode collapse will be even worse for a skew data set, I'm going to talk about the objective function for the generator for a moment. This is the cost function of the generator as a function of that realism score that the discriminator will give to each of its inputs. So if we have a skewed training distribution, the likelihood that the discriminator will assign to either mode will not be the same. This is a pretty trivial fact because this is just saying that the discriminator will be better for examples that it sees more often and worse for examples that it sees less often. This means that if we have a generated sample that is corresponding to a major mode in the original distribution, that the discriminator will be better at realizing that this is a fake sample. This also means, on the other hand, that if we have a generated sample that corresponds to a minor mode, the discriminator will call this more real. And this loss function gets flatter as the discriminator thinks images are more and more real. And a flatter curve means smaller gradients and less feedback from the discriminator. So trivially, the generator will just have less of a chance to learn to create images that don't exist as much in the original training data set. So it'll create these images much less often. So as I mentioned earlier, mode collapse is where the diversity of the generated distribution is much lower than the diversity of the original distribution. The way that we can measure diversity is to take the support of the probability distribution. So the support is the set of unique values that a random variable can take on with non-zero probability. So if you were to have a simple probability distribution function like this, the support would be the highlighted parts of X where the probability is not zero. For facial images, we can measure the diversity or the support of the distribution by looking at all of the different combinations of high-level features. So high-level features could be position, lighting, expression, gender, race, accessories, hair color, really any high-level feature you can think of, as long as there's a combination that exists in the actual data set, so there's an image of it, it's part of the support of the distribution. This would be pretty hard to measure though, since the support size will be exponential in the size of features. So to verify and characterize how mode collapse is more severe for skewed training sets than for uniform ones, we will use the Clever dataset. Clever is a dataset of objects where you can create certain objects by a 3D modeling software, Blender. It's designed to allow people to artificially control their biases in their dataset. So this is a synthetic dataset controlled by 3D modeling software. The framework to use a dataset from Clever is presented by Zhao et al. And they will project the support of an original and a generated distribution into 2 dimensions from the 2-object Clever dataset. So we only have to focus on how the GAN characterizes shape and color. So if we only look at this 2-feature dataset and we uniformly distribute it, we can have a heat map with the distribution as shown in the left. So if both objects are allowed to take on 3 shapes and 3 colors, red, blue, and green, and sphere, cone, and cylinder, then we can have 81 different classes. So if we train a DC GAN so that it sees 988 examples of every single class, so a uniform distribution, on 3 initializations and sample 1,000 from each generative distribution and annotate the 3,000 images, we should be able to see what the generative distribution will look like. And on the right is our generative distribution. Now, it's not quite uniform, and there's certainly a lot of mode collapse happening here. If we look at the 4th column, the generator seems to learn to create 2 cylinders much more than it learns to create that 6th column, which is where it learns to create 2 spheres. However, the generator does learn to create all of the modes, and it does a decent job at spreading around the probability mass to all of the classes. We want to compare how the generator performed in the uniform training set to a skewed training set. So in this training set, we also have a distribution marked by the heat map where we have one minority class, which is in that left corner on the top, has only 1/9 of the total probability mass of the most majority mode, which is on the bottom right corner. So we only show 330 examples of some classes and almost 3,000 examples of another class. So we again train a DC GAN on 3 initializations to create 3 generative distributions and sample 1,000 images from each, and we annotate all of them. And this is the generative distribution. There is some very severe mode collapse happening here, as we can see that the 2 classes that got generated the most got generated almost 200 times each, one even more than that. And what's more important is that the minority modes are extremely underrepresented. Even though we had 3,000 examples, there were some classes that were only generated once and other classes that were generated only a handful of times. And we also noticed that the minority in the original training set is also the minority in the generated training set, the generated distribution, and the majority values in the skewed training set is exactly where the new highly collapsed modes are in the generated distribution. So we can see exactly how a generated distribution mode collapses from a uniform training set as opposed to a skewed training set. So far, this work has only investigated DC GAN, which is the most popular unconditional variant of GAN. Unconditional variants solve a problem of pure generation, and this means that they take in some semantically meaningless input, such as random noise, and they create something semantically meaningful, such as an image, all from scratch. There's another type of variant that is also very popular on GANs, and it doesn't quite perform image generation, but rather image-to-image translation. These conditional GANs are conditioned on an input, so they're only moving images across domains. So in this case, we can see a generator converting zebras to horses, but we could also do something like daytime photography to nighttime photography, or maybe perhaps a landscape image to the same landscape, but painted in the style of Monet. We might expect that a conditional GAN wouldn't underrepresent minorities in the distribution, because if it's already given an input image of something like a non-white face or a female face, it would have to actually transform these faces to be white or male in order to underrepresent them. But unfortunately, that's exactly what happens. And we show a case study with a Snapchat selfie lens that is presumably GAN-based, and we'll find that it actually ends up lightening the skin tones for women of color. So the Snapchat selfie lens that we look into is called the My Twin selfie lens, or colloquially known as gender swap. Now, one thing that I should say is that Snapchat doesn't actually publicly release how these lenses work. So we don't have the architecture or the implementation of this Snapchat selfie lens, but it's a common consensus in the machine learning community, the tech world, and just the world of lay people who are interested in the app, that this uses something like CycleGAN or some other variant of a conditional GAN. And the rationale behind this is just that CycleGAN was already being used to perform gender swap from image to image translation from male to female faces before the Snapchat filter came out. And as far as we know, there isn't actually another technology that can successfully perform this translation across genders. So here are the results when we ask different women users of Snapchat to send in their selfies before and after using the lens. On the top, we have non-white faces before and after using the lens, and on the bottom, we have white faces. So we want to characterize how the skin color has shifted before and after using the lens. So we will classify each face into one of the 66 skin tones developed by the L'Oreal research team. So we match the average pixel value in a highlighted section, which is just a rectangle spanning both cheeks, to the corresponding color in the L'Oreal palette. And we will measure just the horizontal shift in these classifications. And the horizontal shift indicates lightness. The palette also will have another dimension for vertical shift from the warmth or coolness of skin tones, but since we aren't worried about that, we will ignore any vertical shift. So the horizontal shift results are depicted under each of the figures. So for the non-white faces, the selfie lens almost across the board lightened everybody's skin color by exactly one shade on the palette. And for the white faces, it acted pretty arbitrarily, not changing the skin color classification for a couple faces, darkening them for another couple, and lightening them for another couple. We could always write off the arbitrary result as just variance in the conditions that these images were taken, since these were just selfies sent in by users. This could be due to lighting changes. But we don't see the same kind of arbitrary result for the non-white faces. There was only one case where the Snapchat selfie lens didn't lighten the skin color by one entire class on the palette, and that was where it just remained the same. It never darkens any skin colors as it does for the white faces. So we can see that there is still some consistency in how it performs with the non-white inputs. If this truly is a GAN-based application, this means that in order to fool a discriminator into thinking that an image is of a woman, the generator has to learn to create lighter skin tones when it's given darker skin tones. You also might be wondering why I asked women to send in their selfies using the gender swap filter made for women. Well, it's true that these were most likely trained on a GAN that will perform image-to-image translation from male to female or female to male. The GAN will also try to minimize any changes it makes if an image is already in a certain domain. This is a minimization of an identity loss. So if I were to ask CycleGAN to translate an image already in domain X to an image in domain X, it shouldn't actually change the input at all. So the fact that it feels a need to change the actual skin color just goes to show that it didn't quite think that the discriminator would have understood that it were from the female domain otherwise. We make our own selfie lens of sorts by using our engineering professor dataset. So we ask a GAN to take an image of a non-engineering professor face and transform it into an engineering professor. So if mode collapse will happen, that means that it will probably end up taking faces that are feminine and converting them into masculine faces, or faces that are non-white and converting them into white faces. So we show that a conditional variant of a GAN trained on the engineering faculty dataset biases its outputs to make them lighter and more masculine, just as the unconditional DC GAN did in our previous experiment. Oh, and the dataset that we're using for the non-engineering professor face is thousand images of celebrities. So we train a cycle GAN on a balanced data set of celebrity faces and engineer faces. And here are some illustrative results. So this is a set of female celebrities, and what the janitor imagined was their engineering face counterpart. And we can see that it really does learn to create more masculine features from when its input is a face with feminine features. I also want to highlight that the GAN does pick up on some other biases that aren't gender and race. So in this case, we can see that it actually learns to create glasses on the image. And that might be because the engineering dataset also has many faculty headshots where the professors are wearing glasses. But just to make sure I highlight, this work is not to mention any bias that the GAN could be picking up on, but rather only the sensitive biases. People aren't discriminated in academia for having or not having perfect vision, but they are discriminated against for gender. Or in other cases, we can see that the janitor learned to age up these women so that they looked a little older to fool the discriminator into thinking that they were professors. The same result happens along the dimension of race. Here we have a set of non-white celebrities and what the janitor imagined that they would look like as their engineering counterparts. We again see that the janitor is picking up on some non-sensitive biases. So we see that it converts sunglasses to glasses. And we also see some place where it fails, since the janitor doesn't really know what to do with faces where the image is not of a smiling face, since most of the faculty images are headshots where they're posed and the engineers are smiling. So in an action shot of a face that doesn't have a smile, it kind of erases the mouth entirely. But the more important thing to note here is that it lightens the skin tones. And in some cases, it seems that the only change it even makes to the face is just to lighten the skin tone. So this is a janitor's way of saying that it won't think that it can fool the discriminator with a face of a non-white person into thinking that it's an engineer. So the only way that it can try to fool the discriminator into believing that an image is an engineer is to lighten its skin tone first. This bias amplification isn't just for faces. We were only using this as an illustrative example. Really, it generalizes to other domains as well. One of the domains that we're most wary of is when machine learning practitioners have been using this GAN-based data augmentation approach for medical imagery. This makes sense since medical imagery is a domain where the data sets are usually not balanced. It's very infeasible to collect sufficient unhealthy examples since these don't exist as much in the real world. So two works that have received praise, these were both published in an IEEE conference in 2018. The first one is a generated image of a chest pathology x-ray, and the second is a generated image of of liver lesions. And they were using this to be able to balance their classifiers so that there were an even number of healthy and unhealthy examples. And while it's true that this approach could be used to bring balance along a particular axis, in this case, they can just generate more unhealthy examples. So they now have balance between the axis of healthy versus unhealthy. It's actually simultaneously amplifying biases along others. And since medical imagery still represents humans, it's pretty dangerous that it could be amplifying along social biases. We don't want to underrepresent any groups by their age, race, ethnicity, background, family history, whatever in our medical data sets. So we're urging practitioners to exercise caution when they're using this technique, especially in an application where the data set could be skewed along sensitive social features. It would be bad enough if the generator was just capturing all the real world biases and perpetuating them, but it goes a step further to even worsen the biases that exist. So before I conclude the presentation, I would just like to make some acknowledgments and extend my gratitude to Dr. Rao. Thank you so much for introducing me to artificial intelligence with your Intro to AI class and for piquing my interest. This was something like almost 3 years ago. And thank you for taking me on as one of your only undergraduate researchers in your lab the semester after that class, and for being my very first mentor in the world of research and academia. Thank you so much again to my committee members for being here today, Dr. Juan Lu and Dr. Lydia Manikonda. Thank you so much to my co-authors of this work. This research was not done alone, so I extend my gratitude to Alberto Olmo, Shelik Sengupta, and Lydia Manikonda again. Thank you so much to all of my lab mates, past and present. Thank you to my parents, my sister, all of my friends. Thank you so much for being here and representing several different time zones. And thank you so much to all of the mentors I've met along the way. This paper that we wrote, we submitted to the International Conference on Web and Social Media. The paper is in a tiny corner on the left. We have gotten several citations on our paper. And on the right, I picked an excerpt of a relatively nice review from ICWSM, although our paper did not actually get accepted to the conference. This reviewer believed that we had an important problem with some profound insights, and we gave light to some serious implications in a timely manner, since GANs are now extremely popular in these applications. So to summarize and conclude my presentation, as a result of mode collapse, GANs, whether they're unconditional or conditional variants, are going to amplify the biases along a direction that exists in the original training set. We can show that this amplification of skew happens when we train GANs on facial data sets and show that they will bias along race and gender. The most important thing to note here is that all data sets are skewed unless they're carefully designed not to be, at least along some axes. So it's extremely hard to avoid bias. We just want to urge machine learning practitioners to exercise caution when using GANs to generate synthetic data when these biases could exist along sensitive features. And if there is no way around balancing a data set along these sensitive features, perhaps just asking them to stick to some traditional data augmentation techniques that don't use GANs. I'd now like to open the floor to questions from my audience.
Okay, great. Thanks, Niharika. So right now, anybody, including the audience as well as the committee members, can ask questions. Go ahead, just unmute yourself and ask questions.
Hi, Niharika, this is Tejas. So thanks for the talk. I had two questions. One is technical. So the first question is, I've seen Wasserstein GAN being used as a de facto GAN in vision, especially for avoiding mode collapse. So did you have any experiments on Wasserstein GAN, which is essentially a general case of Earth movers distance? And the second question was about biases. So in my own work, I've seen biases like linguistic biases in visual question answering, where most images about sports are about tennis. So if I ask the question, what sport is being played, the model always says tennis, even if the image is about basketball. So this is more of a machine learning problem. So one way to solve it is to collect diverse data sets, but what would, according to you, be an algorithmic way to avoid this problem? Thanks.
Thank you so much for your questions. So you're addressing your first question. Yes, there are actually a few different architectures of GANs that reduce the mode collapse problem. However, this work was aiming to focus on two of the most popular GANs, since these are the ones that machine learning practitioners are using. There are some architectures of GANs that do very well in terms of capturing the original data distribution, but they don't quite have a good quality of images that can come out. So there are a few architectures that use Wasserstein distance to minimize as opposed to a different divergence metric of distributions. So some of these are the unrolled GAN or the VGAN. These don't actually create images that any human would mark as realistic, and sometimes they'll look not much better than random noise. So this work focused on only using the scalable architectures that are most commonly used by machine learning practitioners, since there are so many, since there are hundreds of different GAN variants. We limited our research to just investigating those two. And I'm sorry, can you repeat your second question?
Yeah, the second question was more about the fact that this bias exists is because the data set is skewed towards the majority. So what would be an algorithmic way to avoid this bias? How do we learn diverse representations without having diverse data?
I'm not sure if I necessarily know the answer to this question, because one of the biggest parts of this work is that these biases could exist along latent dimensions that people don't even know of. So if you wanted to do it algorithmically, you could force a network to create more images along a certain mode. So we can just hardwire it into the loss function for a generative to create more of one mode so that it accounts for the bias algorithmically. But this problem is a little deeper than just being able to algorithmically solve the problem, because these biases exist along every possible dimension of high-level features. So these high-level features, again, they could be things like lighting, or they could be something drastic. So I'm not sure if there's an easy algorithmic solution. I think this work was really just trying to hit home that it is such a hard question to solve. Yeah, I think my answer is just that I don't think this is an easy algorithmic solution. You can't just tell a generator to create more of a certain mode, because you wouldn't know all the modes to identify.
So if I might add a point there, that it's, first of all, I think as Niharika points out, it's not so much, she's not surprised that there are more male looking professors than female looking professors in the generated data, because the original data already had that. She's surprised that even higher percentage of images have become male compared to females. So it's just kind of worsening the already existing skew in the data. And it's not so much that she actually went out of her way to collect data that was sort of biased. This is basically the society that we have, where more of the professors are white, male, balding people. And so now beyond that, if you want to change the data, that would become social engineering, and that's something very much fraught. So I think that's something to keep in mind. I don't know that you can diversify data. The point she's making is that even with your best of intentions, you can worsen an already skewed reality. And on top of it, in fact, people could be careless and wound up actually getting biased data selection, in which case it's even more problematic. So.
Right, thank you. Yeah, that makes sense. Thanks.
Other questions? Just unmute yourself and ask. And the committee members can ask right now, and also they can ask separately later, but feel free to ask. You know, there's sometimes I think the whole point of these is sort of have the discussion that's public as much as possible. When we want to call names, then we'll get our people out and we'll just call Niharika names directly. But anything, you know, that's academic, we should probably do it in public.
So Niharika, I have multiple questions, but I'm going to ask one question, and I think everybody will benefit from this. So for example, when you are talking about the, the L'Oreal skin tone palette, and you were talking about the horizontal shift. Yeah, if you can go to that slide, please.
Oh, it was pretty far back. Let me,
Okay, I'm
there we
sorry.
go.
Yeah.
Okay, no worries.
Yeah, so can you actually talk a little bit about, so for example, I understand, so first of all, like the, I can clearly visibly see that, I mean, we already discussed about this, like how the skin tone and even the hair and various aspects in the filter applied image is changing. But my question is, did you think about any automated approaches to essentially figure out what are the, because we are looking at these pictures manually, but what if you have like a humongous amount of data set and you want to create an automated way to see if these perpetuated biases are kind of uniform across all these newly created or newly generated images?
I think the automated way would be, so in this, we kind of did a pseudo automated way. In this case, we cropped each of the images manually to that highlighted portion so that it only had the cheeks, which was a lot more consistent, and it didn't have the dark parts of hair or eye color. And so we took the average pixel value in each of these highlighted regions, and the average pixel value, we found the closest shade in the palette. But the part that we did manually in this automated approach was we physically cropped the images so that they all had the same highlighted region across the faces. Some automated approach would probably want to segment the image so that it can ignore the eyebrows and the eyes, which have a different color than the skin. Oh, and also the lips, to remove this from the actual image, so we can then take an average pixel value over just the skin on the face. And then the automated approach would be the same. We can take the average pixel value and then map that to the closest shade on the palette, and then it becomes an automated process.
Okay, along these lines, I'm just curious. I know you talked about this, so I'm just curious, like, did you think about any also metrics to measure diversity?
So do you mean diversity along gender and race?
So we know, like, from the data set, we know that, as you mentioned, there are two, like race and gender are the two metrics that we are considering bias here. But did you think about, like, I mean, you also mentioned that, like, there might be numerous biases hidden in the images, but I can't see those things. But in fact, like, is there any way that we can actually propose a diversity metric that can, because right now the images are coming from 47 universities from US, but if you have like a humongous amount of data set and we want to see some sort of like a diversity measure that's there as like a ground truth data, you know what I'm saying?
Yeah, so would this diversity metric be allowed to have the features that we might not care or think about, such as lighting and facial expression? Or are so the way that we would do this is probably, let me go to this slide. So one of the ways that we can measure the diversity of a distribution is to measure the support size. So the support would be the different combinations of high-level features. So all of these features could be the combination of lighting, facial expression, gender, race, age, hair color, eye color, all of the high-level features you can think of. And the way that you can actually measure the support size, in this paper by Aurora and Ristevsky and Zhang, they calculated the support size, or a lower bound for the support size, by using the birthday paradox, which is, actually, let me go to this additional slide that I have here. So on the right, in the text box that's on the bottom right, for a probability distribution that has a support size n, the birthday paradox says that you'll find a duplicate with high probability, so over 50%, from a batch of square root of n. So the way that they use this birthday paradox to actually calculate an estimate of the support size is to just see what batch size they need to have in order to find in order to successfully find a duplicate over 50% of the time. And in this case, a duplicate is not like an exact copy of an image, but something where you could use just a k nearest neighbors approach to find some very similar images. So if you had a blonde white female with short hair and blue eyes smiling with the light on the face, you would be able to detect that two of these images look identical and mark them as a duplicate. So whatever batch size you need to have in order to find this duplicate with high probability, you would just take the square of that batch size, and that is your estimate of your lower bound on your support size.
Okay, thank you, Niharika.
Yeah.
Okay, I have questions. And
yeah, thank you, Dr. Leo.
it's now you select the best, the 47 engineering schools. It is
right.
Itself, it is biased selection.
Right. Yeah,
So,
that's true that this is a biased data set because these universities aren't, we don't know how the diversity of the universities look, and we don't know what the recruiting patterns are, but we are completely relying on the idea that we're depending on what type of professors these top 47 universities are recruiting. But I think the grander point of this is that when machine learning practitioners are taking data from places like the web or social media, anywhere that they can curate a data set, it's inevitably going to be a biased data set. So I wasn't intentionally seeking out a, I was looking to just make the claim that if we have a real world data set, which usually is very biased, that the generative distribution will actually even further those biases.
It's very good. The work and it is very interesting. Okay, you have this human machine bias, and also you have this Tucker's. You use the Tucker's, right? And also there's a Tucker's bias. And it depends on how many Tuckers you select. Okay, so the point here is, you point out a real problem, okay? It seems impossible to solve, right? So you just you provide, this is a very good one. Actually, I would like to look at it. And you didn't provide the slide number, so it's very difficult for me to point out which one.
Oh,
okay?
Sorry.
It's okay, it's okay. This is the one, you read my mind, okay?
Okay.
I wanted this one. Yeah, if you look at this, right? And the original one versus the GAN generated one, they are skewed so much. And why? So supposedly, if you skew so much, can you still generate realistic in terms of the training data you have, the realistic images in terms of the training data you have?
Right. I actually want to move one slide over.
Sure.
And we didn't do a test on how realistic images looked across whether they were the majority face or the minority face, so a male or a white face versus a female or non-white face. But we can kind of get an idea of how realistic an image is based on how confident the Turkers were that an image was of a male or female. So the faces, it's true, don't look photorealistic. They definitely look like generated faces, and in some cases they're not too realistic at all, but we can still kind of ascertain how masculine or feminine they look. So DCGAN does not generate realistic faces. There's just no way that we know how to scale GANs to start from something like random noise and generate an image that is extremely realistic in terms of the training set. The GANs that have been created that create photorealistic images are conditional variants. So they take inputs and they change the input values. They take actual input images and they will change the values of input images to create a novel output image. Sorry.
So no, it's fine. It's fine. The work itself is interesting. I just want to know a bit more. For example, so if I insist that images I train, I get GAN generated must be very close to the quality of the original in the training data. So what I still see so much bias. And my point here is this: you can train forever, right? So when do you stop? You just stop because of like a discriminator cannot tell the difference. You stop.
Right. So the way that you would create realistic faces, if that's your goal, is not to use DC GAN or any other unconditional variant. So the state-of-the-art GAN for faces in terms of how photorealistic the faces look is called style GAN. And that's the one, if you go on thispersondoesnotexist.com, I think it'll create a very high resolution face that looks really indistinguishable from a regular human. This is a conditional GAN that takes several different inputs and will take these high level, low level, and like medium level features. So it might take the skin texture and skin color from one image and take some finer details from another image. So these are conditional variants of GANs. And I would hypothesize based on the results of this experiment that we would still see a lack of diversity, because we've shown that even conditional GANs can suffer from mode collapse. This is where they would underrepresent minority features. And we know that this happens because they'll literally convert minority input images to majority output images. So they'll actually convert a female face to a masculine face, or a darker skin tone to a lighter skin tone. So while we didn't do any experiments on style GAN, this is the state of the art photorealistic face generator.
It is okay.
We would
Your work
imagine.
is fine. Your work is fine. Okay, you don't have to do you work on every generator. You have a hypothesis. You clearly demonstrated what's the result of this hypothesis. Okay, so now another question is this. So you only know what you know, right? So the bias, and like you have race and gender in the beginning, but then when you talk about the celebrities, somehow age is there. So in the first set of example, like this result, only gender and race, and age is not there. So my question is, because you don't know about the age, right? In this set of
right.
experiments.
Yeah, it's true. This work was only scoped to race and gender, and I meant to bring up age as something that we can kind of visually see that a generator tries to. It's one of those biases that the generator may be picking up on, just like how it may be picking up to learn to create glasses and images. This work is not meant to give a fully scoped example of all the social biases that could exist, such as age or even wearing glasses. It's just that the hypothesis that I made, let me go to the very...
You did that. You're very smart, okay? You picked a very good hypothesis to work on, okay? So there's no, I don't ask you to consider all the biases, okay?
Right.
So you already proved your point. It's good.
I do want to make the hypothesis that, again, will pick up on potentially any bias that could exist. And I think that's something that's important. So even though we only looked at,
right? That's the mode collapse.
Yes. And I think that's important because when we're talking to actual machine learning practitioners, they don't necessarily know the biases that exist in their data, especially if it's something like medical imagery, where we can't easily detect where social biases could exist. So if we have a medical image of a male who's non-white, we can't necessarily distinguish the medical image of a male who's white, but those social biases can still exist. So we just want to make the claim that these biases, or this bias exacerbation, can happen over really any bias, whether it's visible or not visible, and that these biases can be hidden in the data set. So this hypothesis does make a claim about GANs picking up indiscriminately against any skew, but we only choose to investigate gender and race because it's easy to see.
Yeah, and so you paint a very dismal picture for GAN, right? Basically, so yeah, it is. It's fine. It's good, huh? And for the image, this medical imagery, I'm so surprised. The people really try to generate fake images to do real study.
Oh yeah, this is actually extremely common. And
That's
AI for
really...
healthcare is very popular right now, especially among giant tech companies.
Wow, this is like I think you should help her out to write the Hill article about this. You will get an instant fame.
Dr. Rao was actually the one who brought this to our attention. This was the motivation of the research.
So actually, I told you I won't ask questions, but I'll ask this one mostly
Sure.
to make other people also think about this. So looking at this medical data, it's not just social bias. I mean, actually, one of the points you're making is there may be social bias in the data. I think social bias is something that at least after the fact, with some study, you may be able to establish. So first of all, let's just think in terms of precision versus recall aspects of this. If you have an image that doesn't even look like human, you can easily realize that. That's unrealistic human face. That is lack of precision. You can capture that. If on the other hand, you create a distribution of faces and the end user can't tell whether that distribution is reasonable or not. They would have just thought this is how, professors look. And at least for that, you had to then carefully study, but with, Turkers and so on, whether in fact there was a higher percentage of males in the generated distribution than even in the original data, okay? Now, so first of all, recall is always harder to measure, okay? So if you lose precision, people can measure. If you lose recall, people don't know what they don't know, okay? And to some extent, I think of your work as sounding a cautionary note that bozos, you might actually be missing things that you don't even know you are missing, and you have to keep that open possibility. But having come to here, it's not social bias. It could be any kind of, so imagine in these x-rays of COVID x-rays, let's say something, this looks like the one on the left-hand side looks like the COVID x-rays. It turns out, let's say that there is like a minor mode in the way the images are that has nothing whatsoever to do with race, gender, age, none of the sensitive attributes, quote unquote, none of the social justice warrior attributes. And yet they wind up, basically there's a mode for, there's a more of the images are of one particular mode, the other is the other particular mode. And when you're generating, in essence, you are increasing the imbalance. That's what you're showing. And the doctors wouldn't even know that this happened. And the downstream classifier wouldn't even know that this happened. And then we are being operated upon based on these diagnostic requirements. So I think to me, this actually is a lot more worrisome than social biases, honestly. As much as social biases are, very, at least people are complaining about them.
Absolutely.
Okay, you understand what I'm saying? At least woke people are complaining about them. There are no woke people about what is happening in COVID. This is sort of connected to what, Juan was saying. You don't know what you don't know. We don't actually quite have the full realistic distribution of X-rays for COVID. We just have the ones that we picked. And there may be, a skew in certain non-social attributes in these images. And then when you generate more images, that skew would be amplified, is what you're saying, because of the mode collapse. That is very worrisome, because that could lead to wrong kinds of decisions. And people are just, I basically am very worried, as I'm sure you are, that data augmentation is done by practitioners with very little worries about what happens down the stream.
Yeah, they published that IHP conferences. Then people.
I think I'm less worried about publication. At least publication you can check. It's some random thing that your doctor is applying to decide.
I know.
Google. You can't say, is there a Google Scholar count for this paper that you use? No, this is some random guy sold this software, and they just ran out of data, so generated more data.
Yeah.
And it's not even clear that you can differentiate whether or not, it becomes a question of recall. I mean, do they look like X-rays is a precision? Do they look like the distribution of X-rays that will happen in real COVID situation is a recall?
Yeah.
You don't have Turkers to check this for you. So in some sense, I would say that you rang the cautionary bell based on the somewhat easily checkable attributes of social attributes. They're also hard, but at least you could set up a Tucker study. You cannot even do that here. And you are essentially establishing that there's no reason to believe that this kind of a worsening of skew won't happen in anything other than the social features. It will happen across, and so it likely will be happening for these sorts of things, and you don't even know what kinds of exacerbation has happened. So to some extent, I think this is canary in the coal mine. To some extent, we can at least tell. I don't know that social biases are the only ones. All kinds of biases are being just perpetuated.
Absolutely.
Yeah.
But she did a good job. She did a very good job. Okay, you're very smart to select a good hypothesis to work on. That's very important. Then you try to use mode collapse to explain. So then you can generalize to all kinds of biases, not necessarily social bias.
Right. Yeah. Since mode collapse indiscriminately picks up on any random biases, this can generalize to dimensions that a human wouldn't even be able to identify.
Yeah.
Other questions in the open session? Okay, going once, going twice, going thrice. Okay, then at this point, the participants should please get out of the Zoom room.
Yeah.
Thank you so much, everybody, for joining.
You guys.
There should be only 4 people left, right?
Yeah.
Niharika, I think you can actually kick them out.
No,
Oh, okay.
No, don't.
don't
Okay.
kick them.
She will kick us
They will
out.
not stay.
I'm
Okay,
sorry, I
won't.
should
It
have
looks-
used some.
It looks like people are just heading out.
It
But
seems you have a lot of fans, huh?
I
Yeah.
invited a lot of people to this. This is, I
You
mean,
invited
it's
a lot of people. Okay.
yeah, it's me inviting people who have been
Oh, actually,
influential
yeah,
in any part of college.
I can start,
This is the largest audience I have ever seen. I think 40.
Yeah, I invited a good amount of people to this.
You're popular, it seems. We still have people they don't want to get out. Then you
yeah,
have to follow.
I'll kick
You
out
have
people.
to follow.
You can start. Yeah, just don't kick us out.
Yeah,
suggestion.
I'm not actually sure how to kick people out.
No, I'm kicking them out. Don't worry.
Oh, you're kicking them out.
Rao
Okay,
is
thank you.
okay. We will fail
Now
you.
we are now.
Don't even know how to kick people out. So how
Oh,
can
no, there's this Jagan guy is still there. Out you go. Okay, there you go. Now basically everybody's out. So I'm going to, at this point, stop the recording.
It's okay.
Okay.
No, I think you should, no, this is supposed to be.
Okay.